Uh, Hello, Professor. My name is Sricharan Cherepally, and I'm going to give a presentation for my project for this semester. I'm building an automated defect protection system for metal casting, like a real quality inspection problem in manufacturing. So I'll be comparing two approaches, a classical computer vision method and a deep learning method using real-life industrial dataset. Coming to the next slide, which is why this matters. The casting defects like blowholes, pinholes, and burrs are serious problems in manufacturing. Like if they spill past inspection, you get part failure downstream, which means expensive recalls and rework. Right now, this is most costly by human visual inspection, which doesn't scale well with isn't perfectly consistent across shifts. Since these defects are visually distinct, rough edges, dark voids, this is a strong candidate for an automated computer vision solution. Coming to the next slide, which is the preliminary literature review. This is actually a well-studied problem. There are published work using ResNet 50 based assemble models on this exact dataset. Comparative studies testing backbones like EfficientNet and VGG16 to see which generalizes the best, and other work showing the data augmentation strategy specifically affects how well subtle defect like blowholes get detected. So there's a solid base of prior work I can build on and compare against. Coming to the dataset overview, I'm using a public industrial dataset from Kaggle. About 7,300 images of cast metal parts, each labeled defective or normal. So you can actually see the difference yourself. So, can you by the images in the slide? So the defect one have a rough, jagged outer rim from incomplete trimming and sometimes small dark bits from the surface voids. The normal ones have a clean, even edges with no blemishes. So that visual separation is what makes this a good fit for this project. So coming to the first approach, classical feature extraction. The first approach I considered uses traditional image processing. It thresholds the image to isolate the part's rim and inner ring, extract texture and shape features like local binary patterns, and feed those into a simple classifier like an SVM. The advantage here is it's lightweight and runs easily on a laptop, and it's easy to interrupt why it made a decision. The downside is accuracy is capped by how good my hand design features are, but sometimes some defects might slip through by using this approach. So the second approach is a deep learning method, which is the CNN transfer learning. So where we fine tuning a pre-trained lightweight CNN like MobileNet V2 directly on a casting image after some pre-processing. This tends to outperform classical methods because it learns patterns directly from the pixels rather than relying on features I had to design myself. The trade-off is it needs more compute and is less interpretable, though a lightweight backbone keeps it laptop friendly. Coming to the choice justification, after comparing the two approaches, giving those trade-offs, my plan is to use the CNN as my primary and final model because since it has a higher accuracy ceiling based on the literature and uses the classical approach as my baseline. That way, I get a clean before and after comparison to report at the midterm and the final presentation, which is exactly what required for those milestones. So coming to the last slide, which is the image processing strategy. Beyond basic data augmentation, I'm planning four specific pre-processing steps, which are the contrast enhancement using clay, which makes subtle voids easier to see against the gray metal. And next, the threshold and morphological operations, which isolates the rim from the background. And the next, the canny edge detection highlights the jagged rim boundaries that signal bird defect. And the last one, which is the connected component analysis, which lets me count and measure void regions, turning visual defects into quantitative features which I can analyze. This goes well beyond simple flips and rotations, satisfying the image processing requirements for the pitch. So this is all about the project pitch. Uh, Thank you.